So we'll just continue. We'll continue and take it in such a way that we're going to explain the electronic configuration again. After the electronic configuration, we explain the periodic trends. Rodigi, I didn't expect you to put 11 o'clock today too. At most,
But
at
I
most
thought
10:30. You know
no
now.
problem now, no problem. Anything, we deal with you. No
At most
problem now.
maybe. So
Yeah, no problem, no problem.
all right.
Yeah.
So we are going to cover the periodic table from the rules, electronic configuration. So now no time to take time again. Just let's start. The thing is about this, the electronic configuration. Before it, I tried to give some definitions, some few definitions. We defined what an electron is. We explained to ourselves what do we mean by the orbitals, what are the rules guiding them, and what is the proton, what is the neutron. We stated some models of atom. Let's mute our mic. It's only Prodigy and myself that we are having mic that is not muted. So all others, please mute your mic, please.
Your network is your network is breaking.
My network, sorry. Sorry. All right. So I said we gave ourselves some definitions and some particular illustration about the atom, what it consists of, the models of the atom. We explained some particular theories, some particular histories about atom self. So we talked about the proton, the neutron. We said, according to Sir Rutherford, and what we actually come up on later, he said that the atom consists of a core nucleus, which has the whole of its mass concentrated at. So it's that nucleus that has the mass of the atom concentrated at. So now that nucleus consists of the proton and the neutron. The nucleus, okay, let me start. Okay. The neutron consists of the nucleus consists of the proton and the neutron. Just get another one. I have a pen. So it consists of the proton and the neutron. I'm talking about the nucleus. So the mass number, it is normally the nucleus. The nucleus is the mass number. So it consists of the proton number and the neutron number. But we now add the proton number together with the neutron number. We are going to get what we call the mass number. Sodium has the proton number of 11 because the proton number is the same thing as the atomic number. Atomic number. So an element, the 100th element in the periodic table now, who will tell me how many protons does it have? The 100th element in the periodic table, how many protons does it have? The 100th element in the periodic table, how many protons does it have? Just write it out, please. Thank you very much, King Smith. That's just how it is. So the proton number is exactly the same as the atomic number. So now, it's not actually that proton number that determines atomic number. It is one thing we call electrons. We call them the electron. So this electron must be there while the neutron is inside. Take a good look at what I'm going to illustrate. Yeah, put the light. Yeah, two, three. Okay. So take a good look at this. Chemistry 101. I'm going to draw something now. This is the nucleus of my atom. Around it. So I have one electron negatively charged, another electron negatively charged, another electron negatively charged, another electron negatively charged. So one electron negatively charged, another electron negatively charged. According to this, we can count the electrons. How many electrons do we have? 1, 2, 3, 4, 5, 6. We have 6 electrons here. Definitely, we should have 6 neutrons too. So now it's going to be plus 1 neutron, 2 neutrons, 3 neutrons, 4 neutrons, 5 neutrons, 6 neutrons. I'm sorry, protons. I said neutrons. Protons. So 1 proton, 2 protons, 3 protons, 4 protons, 5 protons, and 6 protons. So this is when the atom will become electrically neutral. If it has 5 protons in its nucleus and it has 6 electrons outside, it is not neutral. You will never see an element like that. It is not neutral that way. So now, what we're saying in essence is that the proton number of an element, what's that? Smart King, what's the issue?
Good evening. Good evening. Can you hear me?
Yeah.
Yes, I'm not understanding it. So
Network.
I'm not understanding it well. I would like to like break it down very well for me because I'm not
Yeah.
understanding. Like
Okay.
I kind of fast.
Let me do as if I'm starting again. Let me do as if I'm starting again then. I have to
Okay,
continue.
thank you. Thank you.
My pleasure. My pleasure. I said that thing we call the atomic number. It is the same as the proton number. Proton number equals to the atomic number, so equal to the electron number. There is one law in physics or chemistry too. We call that law of static electricity. Law of static electricity. It is the simplest law. Law of static electricity states that like charges repels, while unlike charges attracts. Like charges repels, while unlike charges attracts. An atom is a stable atom. An atom is said to be an atom. It is definite because it consists of two opposite charges. What is the first charge? The first charge is the proton. It is positively charged. I gave a hint yesterday, or an hint. I said proton, positive, PP. So neutron, no charge, while electron is negatively charged. So now this proton is positively charged, and it is at the center of the atom. It is inside the nucleus. The other thing is known as the electron. That one is extranuclear. It is not in the nucleus. It is orbiting around the nucleus outside. You can see this is the nucleus itself. This thing is the whole of the nucleus. This one I'm showing here. So all these things now are the paths where electrons are passing through. Electron is negatively charged. The nucleus consists of the proton and neutron. The proton is positively charged. Neutron has no charge. So now the proton is positively charged. The electron is negatively charged. The both of them now counterbalance each other. They are attracting themselves because of the law of static electricity. Or else there will not be this thing we call atom because the electron will fall out. If it is negative and negative, then the atom will not be electrically neutral. Atom will be negative. It will be negatively charged originally. But here it is electrically neutral because the number of protons equals to the number of neutrons. That is the logic. So now, what I'm now saying is that the proton number must be equal to the electron number. If this thing is different, definitely it is wrong. That is, you must have your proton number equal to the electron number. That's when they will counterbalance each other. If the positive is becoming much and more than the negative, definitely it won't help. And if the negative is becoming much and more than the positive, that also will not help. It will be going to one side, you understand? So it won't be balanced. So we are not buttressing so much on this because it's nothing under our topic. Yeah. I only talked about it a few minutes yesterday too. So let's just take it to a serious place now. We won't waste much time. The thing is about the rules that guide electrons filling in the orbitals first. But one thing I want us to know is that here, when we are talking about configurations, we are using the atomic number. We have about 3 types of configuration like that. We have the orbital symmetry. We call it orbital configuration. That is when we use orbitals like this. This is an orbital. This is an orbital. This is an orbital. This is an orbital. So these are the orbitals we are talking about. We now divide this into three. We'll explain everything there. So the second thing is the electronic configuration. It's that electronic configuration that determines the chemical properties of that element. Electronic configuration is the second thing. And after the electronic configuration is what we call the shell configuration. Okay, Rodigi, I thought you mistakenly raised it.
No, sorry. A question, please. So is it possible for the electron should be greater than the proton? Should be more than the
If
proton?
that's after a chemical reaction has taken place.
Yeah. Thank you.
So when the chemical reaction takes place, you now see that the element is not chemically neutral again. It will now become an ion. That's when you see that it is carrying negative charge or positive charge,
Yeah. Thank you.
because the electron has become more than the proton, or the proton has become more than the electron. This one is sodium now. It will lose electron, while electron. So definitely the proton has become more than the electron. That's why the positive is showing on it. The positive has become dominant. It is no more electrically neutral. This one is an ion. It is no
Yeah.
more an atom like this. It is an ion.
Thank
It's
you.
not a neutral. Yeah, have I answered your questions?
Sure, sure, sure. Thank you.
Miss Blessing, speak out. Miss Blessing, you raise your hand. Okay, Mr. Charles.
Oh, yeah, good evening. Good evening. So sorry, I want to ask
Eh?
that you go over this experiment.
You're not speaking out, Mr. Charles. Why?
Hello?
I'm not hearing you well. Hello, I'm not hearing you well. Is it your mic? Are you blocking the mic?
Hello, sir.
Mr.
Please, can
Charles.
you repeat the question again?
Mr. Charles, I'm not hearing you.
Hello, can you hear me now?
I didn't hear you at all.
Mr. Charles, nobody can hear you, please. Nobody can hear you. Maybe you should log out and log in back.
Nobody can hear
Mr.
me.
Okay,
Bankole,
this is it. Shall I just explain again? Maybe the answer
How
will
are you
be
doing?
question. Okay, what of in case of chlorine and neutron number is greater than the proton number? You were here yesterday, right, Mr. Ajayi? We explained this one several times yesterday. I will explain again, don't worry. Okay, so let me do as if I've not explained it before. Let's explain again. This, I said, Prodigy asked a question. Mr. Andrew, he asked a question now. He said, because we said an atom, for it to be electrically neutral, the number of proton must be equal to the number of electron. He now said, is it possible for the number of proton to be more than the number of electron? Or is it possible for the number of electron to be more than the number of proton? I said, yes. So, but when that happens, the atom is no more an atom. It becomes an ion, ion, ion. It carries charge. So if it becomes an ion, that's when you will see it having all the that is the is my network good like this. Are you hearing me, please?
No.
Hello? Sorry, my network fluctuated. I think it's stable now. Okay. So I said the sodium ion we have here now, this is an ion, sodium ion, not just a sodium atom. If it is a sodium atom, then it is electrically neutral. But this is the sodium ion. Why is it a sodium ion? Because it has lost one electron. Because it loses one electron, the proton has become more than the electron. Normally, proton and the electron are always the same numbers. Proton is positively charged, electron is negatively charged. But now it has lost one electron. Because it loses that electron after reaction, the proton now became one more than it. Before, it had 11 protons, 7 electrons. After losing one electron, the proton still remained 11. Now the electron became 10. So proton is already leading over the electron. That's why the one it is using to lead over it, that's why it is getting it out. Proton. That's the plus. Proton is positive. As for chlorine, before reaction, chlorine atom consists of 17 protons and 17 electrons. After it's reacted, chlorine becomes an ion. So that ion now, the proton is still the proton, is not altered, but the electron changes. Chlorine So adding one more electron to the electrons, that's 17 electron before, it becomes 18 electron, and the proton is still 17. That's why the electron is showing that it is already leading the proton. That's why you have -1. Go to the case of aluminium 3 plus. They will write aluminium 3 plus after reaction. But if you are writing aluminium normally, you write only An. This is aluminium atom. This one is aluminium ion. Aluminium ion. Because the number of proton is already different from the number of electron. It has lost 3 electrons. So the proton is already lacking there. It's already leading over the proton or over the electron, and the electron is lagging. Mr. Charles, okay.
Hello, I hope I can be heard now.
Ah, still the same thing. But try. Let me see if I can try to.
Okay, can I be heard now?
Exactly. This is perfect.
Oh, okay. So I want to ask, you just made an example concerning aluminium now. That after
Yeah,
aluminium goes through a reaction,
yeah,
it becomes aluminium 3 plus, which means
yeah.
it loses 3 electrons. Am I right?
Exactly. You're right, Mr. Charles. You're right.
Yeah, I'm asking that, is it in every reaction that aluminium does behaves like this, where it loses 3 electrons, or it depends on what it is being reacted with?
All reactions, aluminum will lose 3 electrons because it will always react with non-metals, and it will lose 3 electrons. In some cases, it reacts with some metals like sodium, aluminum, and hydroxide, also all this zeolite stuff. But it will still act this way. That's all metals. They will always act their unique way, except transition metal. It is transition metal that have more than one oxidation number. So the oxidation number of aluminum is +3. This is the meaning, because it is always losing 3 electrons. That's when you say aluminum, its oxidation number is what? Plus. The network. What you have something to
Okay.
ask? The
Yeah.
network is
So
doing.
I just want to confirm something. Automatically, if an
Yeah.
element is having a cation, that means
Mm,
it's showing that that's the number of electrons the element loses, right? And if it is
exactly.
having anion, that means that's the number of electron the element gains, right?
My service.
Do you get my question?
No. If it is
I sh-
an I got
Should
it,
I
but
come again?
I think my service is fluctuating seriously.
Should I come again? Can you hear me?
He says network is giving him problems, so just wait. When he's back,
Okay.
then you can get
Okay.
back to you.
Thanks, Beatrice.
Please, what's wrong, bro?
Àwọn náà fẹ́ fi keyboard já kínní.
Please, let's be patient for him. He will join us soon. I think he's having network issue.
Okay.
Can anyone
Yeah,
hear
I'm
me?
here. I'm here now. I'm here.
I think
I'm
it's
sorry, the network is just competing seriously. So you were asking a question about the cation and the anion.
Ali, can you
The
hear us?
cation positively charged, positive charge.
Ali,
So
can
that's
you hear
positively
us?
charged.
Can you hear me?
I can hear you.
We cannot hear you.
Network. That's not
But I'm hearing him very clear. I don't know. I can hear you loud and clear.
I'm hearing clearly. I'm hearing clearly. Yeah. I hear you.
Can hear him clearly
Maybe
too.
he's the one that is not
Yeah, I
hearing.
can hear you. I can hear you, Ali. I can hear you now.
The guy just want wine you small. We can hear you.
No, I can't hear him before, but I can hear him now.
Continue, Jerry. So sodium ion is, this one is cation, it is positively charged. So it is positively charged means it is losing electron. That's why its proton becomes dominant. Negatively charged means it is gaining electron. That's why the electron becomes dominant. That's why it is negative that is showing. So a cation is positively charged and anion is negatively charged. Those are the two types of ion we have. So aluminium is having three electrons being lost from it. It loses 3 electrons. That's why it is a cation because it is losing electron. That's one, and it is having oxidation state of +3. You should note that straight. So someone asked the question that the mass number of chlorine is 35.5. I explained this thing yesterday several times. It's just a pity we don't have the video. That's why I have to come back again. So the thing is this: chlorine is an atom. It exists in nature. It's an element. It has several atoms. So these atoms exist in nature, 2 to be precise. We have atom of chlorine, that is chlorine. You know the atomic number is still always the atomic number. Chlorine 17, chlorine 17. So this one has the mass number of 35, and this one has the mass number of 37. Are you with me, guys? Are you hearing me now? So
Sure.
Yeah.
Yeah, we can hear you.
Good. All right. So now one chlorine is 35, mass number of 35. Another chlorine is mass number of 37. So this one that is mass number of 35 exists in nature for about 75%. And this one exists in about 25% of the atmosphere or the nature. So now this one is more than this, but we can't just neglect 25%. It's not 2%, it's not 2.55. We can't just neglect it. So, but there is something that accounts for the difference in their mass numbers. That thing that accounts for the difference is what we call the neutron number. The proton numbers will always be the same. This phenomenon now, it's known as isotopy. Isotopy. That's when they have the same atomic number but different mass number. That means they will have the same chemical properties but different physical properties. Because the atomic number accounts for the chemical properties of an element. So now some mathematics calculation or some arithmetics have been done with this. We have 35. Okay, Mr. Charles, let's hear you first.
Sorry, please come again concerning that isotopy.
Okay. And then isotopy is the existence of two or more forms of a particular element, two or more forms of atoms of a particular element with the same atomic number but different mass number. They will have the same atomic number but different mass number. Do you understand now? Chlorine now, we have chlorine of 17, chlorine of 17. You can see that's the same atomic number, but they will have different mass number. This one is having mass number of 35, and the other is having mass number of 37. So what now accounts for the difference between them is what we call the neutron. You know, we said mass number equals to neutron number plus proton number. So their proton number, as we've said, is always equal to the atomic number, always equal to the electron number. That one is fixed. The atomic number cannot change, as we all know, right? It is fixed. But the neutron number with elements, it can change anyhow. We can think it is just 2, and it's not 2. Though after it's been gotten, it became fixed, as we all know. But it's not just what we can what do we call it? What we can predict. We can't just predict the neutron number. It comes with some calculations. You know, we can predict proton number now by saying atomic number is 11. So definitely proton number should be 11. But neutron number, since we can't predict, we can't predict it. That's it. We'll have to do the calculation if we want to get it. So mass number of this one is 35. The reason is because its neutron number is 18 and the proton number is 17. Add them together, you get 35. But mass number of this one is 37. The reason is because its atomic number, which is the proton number, doesn't change. It is still 17. But the neutron number became 20. So and 20 plus 17 gives 37. So what accounts for the difference, or what accounts for isotopy in general? The reason for isotopy is the difference in the neutron numbers of the atoms of that element. These are two atoms of chlorine. The element is chlorine. So these are two atoms of chlorine. Atomic number. They have different mass number. So now, how they got Mr. Smart?
Sorry, I am not understanding this stuff very well. This part where you are now, this clearing. I'm not still able to understand this well. Please, sorry, can you explain it from the isotopy part?
Okay. All right. I've had you. I'll come again. So I said isotopy, that's the phenomenon whereby elements of atoms of the same element, you heard that point. They are atoms of the same element. That means they will have the same atomic number, but having different mass number. These are chlorine atoms. This is one chlorine atom. This is the atomic number 17. This is another chlorine atom. This is atomic number 17. But the mass numbers are different. Mass numbers are different, 35 and 37. We can't just say, let's take 35 and be using 35 as the mass number of chlorine. No. And we can't just say, let's take 37 and be using it as the mass number of chlorine. So isotopy, again, isotopy is the of a element with different mass numbers but the same atomic number. What causes isotopy is the difference in neutron number. Because this atom of chlorine has neutron number of 18. This atom of chlorine has neutron number of 20. That's where the problem comes from. That's where the problem comes from. So now, scientists now did calculation that they must get what they call an average for it. You can't just say we'll be using 37 or just be using 38. Way. So now, this one exists in nature with 75%. And this one exists in nature with 25%. Now do the mass. Look at the mass very well. This is 75 over 100 multiplied by the mass number. That's 35. So equals something. Come back here. Yeah, 37 and 25 over 100 That's 25% in nature. 25 over 100 multiplied times 27. Here now I should have. I beg, who will do the math for us? Who will do the math? Who's going to calculate for us?
So the first one is what?
25 over 100. That's 0.75 times 35. That's 27. 21. 0.75 times 35.
26.25.
26.25. 25, Abi. So, and this
Yes.
one is 37 divided by 4. Okay. 37 divided by 4. That's going to give me
It's
109.
0.25 times 37.
It's still the same thing. Still the same thing.
That's 9.25.
9.25. So now we are going to add the both of them together. By adding the both of them together, we are going to get 35.5. That's where they got the mass number of chlorine. That's where they got the mass number of chlorine. So they are not using ordinary 35 and they are not using ordinary 37. This is where they got the mass number of chlorine from. If they say, why is chlorine not having a mass number that is a whole number? This is the reason. Because it's an isotopic element or it's an isotope. That's the reason. So whenever I want to write chlorine, we'll now write 35.5 chlorine 17. You understand it now? That's good, Mr. Smith. Mr. Charles. That's good to see. Okay. Yesterday I only passed through this thing. I didn't even calculate it. So, but as for us now, we are here. I don't know if we benefited from it. Mr. Gamba, you can mute the mic.
Gamba, please mute your mic, please.
Thank you. Okay, let's enter today's. Don't let us be drawing ourselves back. All those things you asked now, they are not part of the question. We'll not ask us inside exam. All those isotopy. So now we are going to the way we
It may
do the
come out
problem.
before the hydrogen part because hydrogen too have it.
Yeah, I mentioned it yesterday too. Hydrogen has 3 isotopes: proton,
Yeah.
protium, tritium, and the deuterium. So that one is another topic. Now we cannot even reach there. We'll be solving past question. So the thing we have today is just Hund's rule, Habermas principle, and Pauli's exclusion principle. So I think the most important rule for now is this Habermas principle and Hund's rule. So Habermas principle states that in the formation of an atom, Habermas principle says that in the formation of an atom, elements fill the orbitals, electrons fill the orbitals. Electrons fill the orbitals. When I speak slow, I even often forget what I want to say.
Sorry, please start again. The principle definition.
In the formation of an atom, electrons fill the orbitals in order of increasing energy level. That's all. Electrons fill the orbitals in order of increasing energy level. In the formation of atom, electrons fill the orbitals in order of increasing energy level. That's all. That's Habermas principle. So what are these energy level? We have the first energy level, second energy level, third energy level, fourth energy level. What do we mean by the energy level? This is 1s. This is an energy level. Go to the next line. For those of us that were not here yesterday, this thing is mandatory. You should know how to draw it in case you enter exam only. This is 2s. After 2s, we go to 2p. Go to the next line. You go to 3s. After 3s, you go to 3p. So after 3p, you go to 3d. So we call it the SPDF notation. SPDF notation. SPDF notation. These are the energy levels. So after 3D, we go to 4S, 4P, 4D, 4F. After 4F, we come here 5S, 5P, 5D, 5F. After 5F, you come here 6S, 6P, 6D. After 6D, you come here 7S, 7P. And these three, just all of them like this now, they cover all the elements in the periodic table. Where no S orbital, this is the S energy level. No S level will contain more than 2 electrons. So maximum of 2 electrons in the S. You will never hear something S3 or 1S3, 1S4. No. It is only 2. The next one is P. It will not contain more than 6 electrons at max. 6 electrons. The next one is D. Will never contain more than 10 electrons. That's the maximum. And the next one is F. Will never contain more than 14 electrons. We call this notation the SPDF notation. It is the way of filling the orbital. It is known as the electronic configuration way. So this one now, it is just the law that they derive into this thing. Alva's principle. That's what they explained here. Had it been there has been not this pattern, or there had not been this pattern, it would have been very, very hard for every one of us to understand. So, but scientists have actually done a lot. So now let's arrange it the way the energy level comes. This is 1S, your arrow. You can make it same, so you'll be seeing what you have there very well. The next one is 2S. The next one is 2P passing through 2P, passing through 3S, right? The next one is passing through 3P, passing through 4S. The next one is passing through 3D, passing through 4P, and passing through 5S. The next one is passing from 4D through 5P and to 6X.
That's there.
The next one is passing from 5F through 5D, through 6P, through 7S. And the next one is 5F, 6D, and 7P. So these are the, you can see checking the textbook now. You can draw it offhand by yourself. Don't say it's hard. When you enter the exam, you can draw it by yourself. It is something you can derive by yourself now. This is just the way, as simple as this. Miss Joy.
Okay, so now yesterday you were teaching us this one. There was one place that you were filling the orbitals, and instead of 4P, I think you jump 4D. The next level supposed to be 5S, and you wrote 4D or 3D somehow. And you said that
we
we're
were
not going
there.
to see that. You explained something. You said we were not going to see that this
Yes,
kind of
now.
arrangement
I
somewhere
told you now
else.
you're only going to that 3D. Normally, look at it. Normally. I'm coming,
I can
please.
see.
Okay. Yeah, sorry everyone. Yeah, that question you're asking now, I actually answered the question yesterday, Miss Joy. Then you will have, look at 3D, 4P, look at 5S. After 5S, we are now saying 4D again. Energy level than 4D, right? Okay. Me now, according to what we're saying here, we believe that 5S is an energy level lower than 4D because after 5S is when you get to 4D. But maybe they are giving some regards to numerals. Maybe that's what they're just doing and putting the 4D before it, but they are not filling the 4D before it. That's what we did yesterday.
Okay, we can
Maybe
put it
one
before
will fill
5S, but we will not fill it completely before 5S.
it. After you fill 5S, you now come and fill it. You must put it before 5S.
Okay,
It's
okay,
not a time. You don't have choice. You understand?
okay.
All right. We are using this thing now. We'll be filling electrons. We'll be writing electronic configurations. So I'm not really happy that I'm doing this thing again. So, but the first look at Charles.
Sorry, please, which
Mr.
person's
Charles.
rule is this again?
Which persons?
You were explaining the person's
Rule.
rule. You said
Okay,
somebody's rule. Yeah.
I stated it now. Now, Aufbau's principle. It is known as Aufbau's principle. See, I said Aufbau's principle states that in the formation of an atom, electrons fill the orbitals in order of increasing energy level. So this is a derivation for Aufbau's principle. You can see they will fill 1s before filling 2s, fill 2p before filling 3s. So in order of increasing energy level, that's what we mean. Do you understand, Mr. Charles? It is Aufbau's principle.
Please restart this show for me.
Mr. Smart. Smart
Yes,
King.
yes.
All right.
Okay, sorry. Hello.
Yes, yes.
Sorry, I'm not really good with chemistry. That is why. This Avas principle, what's the use of it? I just want to know. Like, what's the use? Because I don't know. I'm not like.
The essence of Bauer's principle is to know how you are going to arrange your electrons. You know, electronic configuration is the most fundamental thing in the periodic table. I mean, the chemical, when we want to define transition metals, we define them as the elements, the metals that have the deep partially filled. You see what we are defining them in terms of electronic configuration. You see how important electronic configuration is. If that's not, we'll never find a way of defining them. So now this man is giving us a rule, guiding us to writing a good electronic configuration. Any other one is a counterfeit. It means that this rule shows the way energy is, the way we are going to arrange it. My brother, if you want to fill this thing without knowing how bounce principle, you start with 1s. You can go and after 1s2, you write 4s2. Why? Because you don't know the rule. But if you know the rule, you'll be able to do it well. That's the logic. So the essence of this law is that it provides the way we are going to arrange the electrons in the orbital, the way we are going to fill the orbitals. That's what it means. Yeah, only you can actually show this reaction just to manage it. Did that answer your question? Okay, now
Mr. Hawa, please mute your mic, I beg.
now if that's the case, we are taking this. This is the first element in the periodic table with atomic number of 1. The second one is the helium with atomic number of 2. Next one is lithium with atomic number of 3. Next one is beryllium, atomic number of 4. I'm going to jump to sodium with atomic number of 11, jumping to magnesium with atomic number of 12. Okay, I'm not jumping. Going to chlorine with atomic number of 17. So calcium with atomic number of 20, scandium with atomic number of 21, copper with atomic number of 29, iron with atomic number of 26. So nickel with atomic number of 24. These are what we will be filling today. We have alkali metals here.
Hello.
We have earth metal, metal, the transition metals.
Hello. Hello.
Hello, I'm hearing you. Are you making a call?
Yeah. Please let's include code. There's something I want to see why doing it.
Now. Good is what?
Thank you.
77.
79.
79. Okay.
Thank you.
My pleasure. Now speak. Please mute your mic, Mr. Awa. Now speak. Mute your mic. Now raise your hands. Speak out. Mr. Awa.
Also zinc, please.
Zinc. Mute your mic, please.
Please
okay. Also zinc. No. You can be doing all those ones yourself. These are the things we'll do. Don't worry. Don't worry. When we do this one, you understand how to do zinc yourselves very well. Don't worry. Let's just but I've added it, don't worry. This is hydrogen. That's the atomic number of 1. So we are filling it. The thing we are using is go to the first energy level. Small, you can understand it this way. First energy level is 1s. So now go and fill it. However, mute your mic now, Abi. Ah, you just listen some. I think only Prodigy can do that for now. Generated delay. Yeah. Okay. So hydrogen has the atomic number of 1. Go to the level 1s1. So 1s. So we're writing 1s1. 1s1. That's the electronic configuration of hydrogen. Nickel 28. Nickel. Nickel. I thought I wrote about or something. Okay, thank you. So helium has the atomic number of 2. So I'm going to fill it 1s2. Lithium has the atomic number of 3. So I'll fill it as 1s2. So I cannot write 1s3 because 2 is the maximum that S can contain. 2 is the maximum. I'll now write 1s2. I'll now go and use the next energy level. What is the next energy level after 1s? It is 2s. So write 2s1. So I've written my 3 complete like that. 2 plus 1, 3. The next one is beryllium with the atomic number of 4. Writing it will be 1s2, that's 2. And the next energy level, 2s2, that becomes 4. So what Smart has been asking since, so if this thing is not there, this energy level explanation, then you will not be able to this thing this way. You will not be able to feel it. That's what we mean. That's the reason. That's why it is there. Okay. The next thing I have here is sodium. Sodium. Everyone, let's concentrate well. Mr. Charles. Okay.
Okay, sorry, please. You said you just while responding to Mr. Smart's question before, you just said
Yeah.
if we don't feel this properly, that we will not be able to like. I want to understand in depthly. I'm sorry, what actually is the applicational use? Let me put it like that. For example, after filling it like this, and we now know the energy level, what is the applicational use? Because I think having that knowledge would also help.
Seriously, you know something, Mr. Charles? I'm really not happy with today's class because it's all what I've said yesterday will be repeating, to be sincere. So I've mentioned all these things yesterday. The applicational use, if you say it that way, is that if as this thing ends in S, this S now, it gives a lot of information about hydrogen. As it has 1 before it gives another information about hydrogen. As it ends with 1, it gives another information about hydrogen. Having 1 before it tells us that hydrogen will only contain the first shell when writing the shell configuration. That means it will be in period 1. These are what those guys used, all those when they leave, all of them like that. They actually did all these things first. So this 1 before S means hydrogen will be in period 1. This 1 after S means hydrogen will be in group 1. S is telling us that hydrogen is an S block element. And we know what S block elements are, the alkali and the alkaline are. Do you get it now? It gives an information about it, a whole information. Go to lithium. Lithium is ending with 2s1. The 1 here is telling us that lithium is in group 1. The 2 here is telling us that lithium is in period 2. The S is telling us that it is a S block element or an S block element. Did I answer your question, sir? Did I answer your question?
Yes, you did. Yes, you did. Thank you so much.
My pleasure, sir. Okay, so beryllium, we're filling beryllium. Beryllium is 1s2, 2s2. It has the atomic number of 4. Okay, we've filled that. We are filling sodium now. Sodium with atomic number of 11. So let's start. That's 1s2, 2 has been out of it, it remains 9. 2s2, another 2 out of it, it remains 7. So after 2s2, what is the next energy level? You should know this thing. By practicing hard before the exam day, you will even know it off hand. So after 2s, it is 2p. You can all see it. Look at the arrow. After 2s, it is 2p. So now come and fill 2p. 2p what? Sodium has the atomic number of 11. So, and p can contain the maximum of 6. Maximum of 6. So 2p6, that becomes 10. It remains 1. After p, after 2p, what is the next energy level? Here come. After 2p, that is 3s. So it remains ordinary 1, Abi. That means 3s1. So this 3 is telling us that this element, sodium, is in period 3. The second thing is that this 1 is telling us that this element is in group 1. The third thing is that it is telling us that it is an S block element. It gives a whole information about it, a whole information, far more than this. So going to magnesium now. I think this should be the last one I'll fill, and I'll jump to one like transition metal. So some people will fill the others for me. Magnesium, filling it. I will have, it has the atomic number of 12. No, just let me take chlorine. I'll jump magnesium. Chlorine. I'm filling chlorine with atomic number of 17. Chlorine with atomic number of 17. That is 1s2. The next one, 2s2. That is 4. Smart is no more here. Okay, so yeah, that's good. So after 2s2, it is 2p6. That becomes 10. So after 2p6, we go to the next energy level. That is 3s2. This is 12. We are going to 17. After 3s2, the next energy level is 3p. So if you can go and check it, you see 3s. After 3s, the thing comes to 3p. So 3p what? Because we need only just 5 now. This is 10, 12. We need just 5. So it will be 3p5. So this p here, take a good look at 3 and 3. Shebi, this is the energy level, 3 and 3. 3s and 3p. That means this thing is in group 2 plus 5. That's because it is 3 that's the coefficient 2. It is in group 2 plus 5, that's 7. It is in group 7. And it is a p block element. This 3 here means it is in period 3. Period 3. So that is chlorine.
Hello?
Yeah.
Hello? Yeah.
Hello, yeah.
It is in period 3 and group what?
Group 7, because, listen please, because the 3 here, this 3 and this 3, you can see both of them are 3. 3 is an energy level. This 3, yeah, this 3, it is known as the principal quantum number. This 3 now, it is the principal quantum number here. That principal quantum number is played yesterday. So 1 is a principal quantum number, 2 is a quantum number. So they have the principal quantum number. So this is 3. So this 3 means anything that is under 3. Had it been stopped at 2, and I have 2 of 2 here. Had it been stopped at 2, I'll add the both of them together. I'll say 8. So it is in group 8. Now it's stopped at 3. I'm going to add the both of them together. That means it is in group 7. Why I hadn't done that before is because we have not been seeing something that comes twice. 3s is only once here. Do you understand? That's why we took it.
Okay,
That
please,
is in group 1.
please, let me, please, the chlorine is 1s2, 2s2, 2p6, 3s2, then 3p what?
5.
3p5. Okay. Like you used to say, you say this 3 means that the 3 means it is in period 3, and the one at the front should be okay. The one at the top, the 5 at the top, should have, according to explanation, should have indicated that is in group 5.
Okay. It's not according to my explanation. According to what you understood. Let me now explain better to you.
Thank you.
The reason I haven't mentioned that is because This one ends at 2p6, right? After 2p6, it was 3s1. So I just said it straight that it is 3s1. So it is in group 1. If I had gotten 3s2 and I now have another 3p something, I would have said something different. So it's that different thing I'm telling you here now. If this thing ends in 3s2, that is, it is just 3s2, I'll say it is in group 2. But now
Okay.
it ends in 3p6, I'll say it is in group 3. Why? Because it is still under the principal quantum number of 3. 3. 3. The both of them are 3. If you are filling the shell, the both of them will fill, 3s and 3p will give you 8. That's what will fill the shell if it is a shell. So the energy level is 3. It is because
Yes.
they are both in the energy level of 3. That's why we must add them together. You understand now? That's actually the reason I
Okay.
chose magnesium, because magnesium cannot still provide that information.
Okay, because
It
they
can even
are
provide it.
in the same energy level of 3. We had the 3
Eh,
together.
yes. So now let's do magnesium. That same thing of process. Magnesium
Okay.
has the atomic number of 2. Yeah, 1s2, 2s2. This becomes 4. 2p6. This becomes magnesium cannot go, Jerry. Magnesium cannot go. Let me write another element here. Silicon. Are you with me, sir, Mr.
Yes.
Bamikoli?
Yes.
Yeah. Another element, silicon. So I'm writing its atomic number. 1s2, 2s2, 2p6. This becomes 10. So you check. If you are not sure of the energy level, check 3s2. This becomes 12, and 3p2. Now it becomes 14. So now I can say because it ends in 3, it is in energy level of 3. So it is in period 3.
Mm-hmm.
That's the first thing. The second thing is that because it is having 2 here, and the 2 are for the energy level of 3, it is in group 4. Do you understand me?
I don't
Just
get that.
because the both of them are under 3 and 3. And even this one is
Okay.
2 and this one is 3, there will be no connection between them. That's
Sorry,
the
sir.
logic.
If I
Okay.
understand, sorry,
Because
sir. I beg, no, Mr. Said.
Okay.
Sorry, what you mean? If I'm getting you clearly, what you mean is once we have the two last numbers, and they have the same quantum numbers, which means we are going to have to add both of them together. Is that what you mean?
Exactly. Exactly. That's what I'm trying to explain. So far they are on the same energy level. That the same energy level means they have the same quantum number. This is principal quantum number, and they are the same here. And even this one is just 2, and the next one is 3. But this one is 3, and this one too is 3.
We can't see what
This
you
one
are
is a
writing
okay,
again.
if
this
we
sorry.
if
This
you
one is
add
a
them
continuation
together,
of
we
this one.
get 6.
Eh?
If you add them together, we get 6.
If no, no, no. It's the thing that is at the top. You're adding the 2 that are at the top. You're adding the 2. 3s.
Okay. Okay.
So that
Okay.
means
That two
this
two.
element is in
Okay.
group 4.
Now I
That means
understand
this
it
element is in group
because they are
4.
in the same energy level.
Uh-huh. And the same energy.
Okay. Okay. But it's in period 3, group 2.
Uh-huh. Group.
Okay.
What do you say?
I mean group 4. Group 4.
Yeah. Period 3,
Period
group 4.
3,
That's
group
it.
4.
You're right.
Now I get it.
You're right.
Now I get
Yeah, you're
it.
right.
Okay. Now I get.
Should
Thank you
I
so much. Hey.